Hello everybody, welcome back to another video. Today we're going to be solving a really interesting problem, so let's get right into it. So for today we have a quite simple challenge here. We're given a semicircle and we're given these two lines and an angle inscribed within the semicircle right here. Our job is to prove that this angle is 90 degrees no matter what these vectors are. So for example, if I decide to have a point here and here, I have to prove that this angle will always be 90 degrees regardless. So let's get right into it. Now, there are a variety of ways of doing this. I know someone who even said that we set this to be the origin, then calculated an arbitrary point right here, and then they found the slope right here, and then they did the same thing here. They found this line, m2, and they said that if m1 is equal to negative 1 over m2, then the vectors are, or not the vectors, the lines are orthogonal, therefore this must be 90 degrees. But for today, we're going to be doing this quite elegantly using vectors. Vectors make this problem quite easy, and you'll see why, hopefully. So let's get right into it. Okay, so the first step of any vector problem is always defining our vectors. It makes it a lot easier to know what we're working with. So I'm going to define a vector of this first red line starting from over here all the way to this endpoint right here, up here, and in this direction, defined as u. Now, vectors can be defined by two things, magnitude and direction. So we have our magnitude this way, and our direction is just this angle theta, but we don't really need this theta for the purposes of this video. Also, I'm going to define this vector starting from right here, and this is our terminal point right here, meaning our arrow is right there. We're going to define that vector to be vector v. Now, if you're familiar with vectors, there's a property of vectors called the dot product, and it's actually an operation we can perform on vectors. So it's a measure of orthogonality between two vectors. And if you're not sure what orthogonal means, orthogonal is just a synonym for perpendicular. So if you've seen this funny symbol, this just means that two vectors are perpendicular or orthogonal and have a 90-degree angle in between them. And we're effectively trying to say that u and v have a 90-degree angle between them no matter what they are in this case. So let's continue from there. Now, as I was saying, the dot product is a really cool property, and if it's equal to 0, that means that our vectors are indeed orthogonal or perpendicular. And here's why. Let's say our u vector is simply a comma b. This is component form. And our v vector is c comma d. The dot product of u dot product v is equal to a times c plus b times d. That's all the operation is. You multiply the components and then you sum them together. If this is equal to 0, you'll find out that these are orthogonal. And I can give an example. Let's say this is u, and let's say this is v. We're going to define u to be 1, comma 0, and v is going to be 0, comma 1. If we take u dot product v, we're going to get 1 times 0 plus 0 times 1, and that's 0. And indeed, that's true because there's a 90-degree angle between these vectors. So this property holds true for all vectors, even in higher dimensional spaces like 3D or 4D. So with this new knowledge, we know that we're trying to effectively prove that u dot product v is equal to 0. Now, let's proceed from here. How can we approach this? If you know something about vectors, you know there's a special formula for calculating the angle between vectors. And we can set this equal to theta for now because we don't know it's 90 degrees. We can effectively say cosine of theta is equal to u dot product v over the magnitude of u times the magnitude of v. I'm not going to be proving this, but if you do know something about vectors, this formula does exist. The issue with this is it kind of gets us nowhere because we can't arbitrarily define any magnitude in this case, and u dot product v is what we're trying to solve for. So this is just setting a relationship between theta and u dot product v. But if u dot product v is equal to 0, we know cosine of theta is going to equal 0 as well. And when is cosine of theta 0? Cosine of theta is 0 when theta is 90 degrees. So this doesn't really tell us anything. We're just trying to prove that u dot product v is 0 anyway. So let's try a different approach. Actually, to help out with the relationship of u and v, we can introduce these two new vectors. So let me try this. I can simply write this as my center of the circle. So if we extruded this semicircle out like this, that would be our center. And I would define a vector going to the same terminal point as all the other ones are. We're going to be calling this vector b. And I'm going to be calling this vector from a. I'll just label this point a. We're going to be calling this vector a right here. So the way vectors work is that they're very additive, if that makes sense. Let me diagram that. If I have a vector u, and this is my vector a, and this is my vector b, I'm starting from this point and I'm ending on this point, and the vectors in between are touching. The vector here and here are touching. So that means this vector plus this vector is equal to this vector, because it's just about your initial point and your ending point. So with this knowledge, we can say that u, our vector u, is equal to vector a plus vector b, right? And we can also define our vector v in the same manner. We can say that vector v is equal to what? Vectors, if you didn't know, they can be moved around in a plane, so it doesn't matter. If I have my vector v here, my vector b, I can move my vector b here as long as it has the same magnitude and the same direction. It is the exact same vector, no matter where I place that initial point. So let's say I place my vector b right here. I just moved it. It's the exact same angle theta, and my magnitude is the same. And I have a right here, but a points in this direction. What if I took a and I reversed it to become negative a? Look at that. This vector now that I just drew is the reverse, or negative, of a. And this vector is v. So that means if we have b and negative a, we can simply add them because we start here and we end here. V, the vector v right here, also starts here and ends here. So what does that mean? That means that the vector v is equal to the vector b minus the vector a. And now we can set up a relationship between these two vectors. We were trying to solve that u dot product v is equal to 0. And we can substitute these definitions in of u and v because this helps set a relationship between them. We're trying to prove that a plus b, or vectors a plus vector b, dot product of vector b minus vector a is equal to 0. Now, vectors have a distributive property and you can FOIL them out, which is pretty nice, and that works out nicely here. So we can simply distribute like this and then like this. That means we have vector a dot product of vector b minus vector a. We were going this way now, dot product vector a again, then we go this way, plus vector b dot product vector b, and then minus a dot product vector b. And we're trying to set that equal to 0, and that's what we're trying to prove, by the way. Let's cancel some like terms here. A dot product b, and then we have minus a dot product b, so we can cancel those out. And we're left with this. We're left with b dot product b minus a dot product a. Now let's take a closer look at what this really means. What does it mean to dot product a vector by itself? Once again, let's go back to the example that I have. Let's say my vector my vector b is equal to some arbitrary value h and k. Okay, that means b dot product b is going to equal h times h plus k times k, which is equal to h squared plus k squared. Now, what is the magnitude of b? The magnitude of b is essentially the length of vector b. In this case, it would be this, but I'm talking about any arbitrary vector. So let me just label a random vector b in this case, like that. If I have my component this way going h, and then this way I'm going k, which is what that vector signifies, x and then y direction, I can simply, what is this line equal to? That's just Pythagorean theorem. We have square root of h squared plus k squared. That means the magnitude, which is represented by these two absolute value lines, of b is equal to the square root of h squared plus k squared. Now, do you notice something here? B dot product b and magnitude of b are very similar, except this one has a square root. So we can say that b dot product b is equal to the magnitude of b squared, because the magnitude of b squared is just h squared plus k squared, which is the same thing we got when we did the dot product of b to b. Now, why is any of this important? We're going to see in just a second. Let's quickly replace b dot product b with the magnitude of b squared. So we have magnitude of b squared, and we can do the same thing here because we essentially said any vector u dot product u is equal to the magnitude of u squared, and we proved that here. So we have minus the magnitude of a squared. Now, what does magnitude really mean? We said that magnitude means length. So if we take a look at this example, let's examine the lengths of a and b. We have a, we have the vector a going from this point to this point. This is our center, and this is an endpoint that exists on the circle, which means that this is actually a radius in length. And similarly, this is our center, and this is also a point that exists on the circle. So we can call this length right here also a radius. And we're calling the length the radius, specifically the length. And the magnitude is dealing only with the length. We're not saying that vector b is equal to r, because that's not true. R is just a scalar value, and b is a magnitude and direction. It's a vector. So with this case, we can say that because we're specifically referring to the magnitude of b, we can replace this with r, because r is the length. That means we're saying r squared minus r squared. And what is something minus itself? It's always equal to 0. So if we backtrack now, just to see what just happened, we were trying to say that u dot product of v is 0, and then we set some terms on how to describe u and v on the left-hand side right here. Then we replaced those in, we expanded, over here, and then we got this, and then using the property of the circle specific to this case, we determined that the magnitudes were equal to r, and r squared minus r squared is always 0, effectively saying our original statement that u dot product v is 0 is true. And because u dot product v describes the orthogonality between vector u and vector v, and it equals 0, that means the two vectors are orthogonal, effectively proving that this angle is always 90 degrees. I hope you guys enjoyed today's video. If I glossed over something, please let me know in the comments. I'm happy to explain. If I got something wrong, please let me know in the comments. I am sure, I make mistakes all the time. So yeah, hope you guys have a great rest of your day. Thank you.